In this video, we are going to talk about exponential function. An exponential function is a function of the form a times b to the x, where a is a non-zero real number. If a is zero, right, that would just make this whole thing zero, and that's not an exponential function. And then b is a positive real number not equal to 1. So if the b were 1, then 1 to the x would just be 1, and you'd just have a constant function. That's the reason for the restriction for that. So the number b is called the base of the exponential function. Okay. All right, so let's look at some examples of exponential functions. All right, so here the first one is 2 to the x power. The a in this case would be a 1, right, which we normally just don't write here. And by the way, some in some later courses, they might just call this an exponential function, b to the b to the x part, and not have the constant part out there. But in our book and in this class, we will refer to exponential functions as some number times b to the x. All right, so here the a is 5.6 and the b is 3.14. Sometimes you will see the base written in parentheses, or sometimes you'll see a dot here indicating multiplication. And the reason for that is because it could be ambiguous if you didn't write that. For instance, right here on this one, if I wrote 32 to the x plus 2, right, then that you couldn't really tell if it was 32 to the x plus 2 or 3 times 2 to the x plus 2. So that's why a lot of times you'll see these in parentheses here. Number one, it would be easier to read, right, and sometimes it's ambiguous if you don't put that. You're not really sure what the base is. All right, here the a is 4, b is 1/2. Here the a is -5, the b is 8. All right, and these are clearly exponential functions. This one you might question a little bit and say, hey, is that really an exponential function? Because what's the story with this plus 2 right here? Okay, so that is an exponential function. So let me just show you how that would go. Right, so if I have 3 times, I guess it was 2 to the x plus 2. Yeah. Like so. That's what I had. So what you can do is to split up this part, the base part, like so. I could write that 2 to the x plus 2 power. I could write it as 2 to the x times 2 squared, right? And now you may say, well, wait a second, why is that true? But really, these are just the exponential rules that we talked about in the previous video. Here we are multiplying like bases, right? The base is 2. So when you multiply like bases, what do you do with the exponents? You add them together. So 2 to the x times 2 squared, right, is 2 to the x plus 2. So by the laws of exponents, these things are exactly equal to each other. Okay? And we know what 2 squared is. That's just 4. Okay? And so now I have 3 times 2 to the x times 4. Well, 3 times 4 is just 12. So this function really is just 12 times 2 to the x. And now you can see that's exactly in that format, a times b to the x over here. So this doesn't look at first like, hey, what's up with that? Maybe that doesn't look exactly like this, a times b to the x. But you can rewrite it so that it looks like that. Okay. And if this exponent is a linear function right up here, then you can do that. This trick I showed you plus another one, possibly, to rewrite it in this format here. Okay. All right. So that one is an exponential function. All right, some that are not an exponential function. This one here is a linear function, right? This one is a polynomial or a power function, however you want to say it. And here, again, the x is in the bottom part, and the exponent is a number. So the base is x, the exponent is a number. That's, in a sense, the dead opposite, right, of a exponential function, because we would need for the 3 to be in the base and the x to be up in the exponent. All right, this one, right, is not an exponential function according to our book and everything, because of the fact that it has a minus 3 as the base. So, you know, if it kind of depends on your point of view, but for us, it's convenient to do that. And so I'm just going to graph that out for you and show you what 3 to the x looks like, right? And the problem is that when you raise negative numbers to some powers, it turns out to be a complex number. So that's what 3 to the x looks like. If you graph out minus 3 to the x, you're going to see it has kind of a crazy looking graph. All right, so you can see it's a bunch of dots and things that look like that. All right, and so the reason for that is because, like I said, if I take minus 3 and raise it to the second power, you know, that's fine. I get 9. Negative 3 times negative 3 is 9. But if I take and raise negative 3 to an irrational power, like pi, well, actually, oh, that's 3. If I take negative 3, right, and raise that to a irrational number, you can see it says undefined. Okay, and really what it is it comes out to be a complex number. So that's why the graph looks like that. You can see that if I look at 3 to the x, right, it looks the same as that for some values, and then if I graph minus 1 times 3 to the x, like that, you can see it looks sort of like the other half there. So that's a kind of a complicated situation there. Need some more math to be able to explain exactly the situation there. So we just will not talk about that and not classify that as an exponential function in our class. This is a quadratic function, right? So not in the form a times b to the x. Same thing here, right? This is square root, right? And then here, so not an exponential function. It's not some number times some number to the x power, and you can't, you know, really write that as such. Okay. All right, so some facts about exponential functions. The exponential function, its domain is all real numbers, so it has no domain restrictions, so that's nice. The range depends on whether the number a is positive or negative, kind of just like I showed you in the previous slides there. If the number out in front is positive, right, then the range will be 0 to infinity. And if the number out in front is negative, then the range will be from minus infinity to 0. So all negative real numbers. All right, you can see a typo right here. The y-intercept of f of x equals a times b to the x is a right here. So this should say, this should be a right here. All right, so for instance, if I graph f of x equals 3 times 2 to the x, we can see, right, that's where the y-intercept is. And if I did 2, right, you can see that's where the y-intercept is there. All right, so make sure you note that that's a typo. And I'll fix that before I post these notes. The function f of x equals a times b to the x has a horizontal asymptote of y equals 0, so the x-axis. All right, so what is the graph of f of x equals a times b to the x, an exponential function, looks like? It kind of depends on whether a is positive, right, and b is greater than 1 or in between 0 and 1. So if a is positive and b is greater than 1, it looks like this, okay? And I already told you that a controls basically the intercept here. And if I look at b, so if I have a times b to the x, so a I'll put at 2, and b needs to be bigger than 1, right? And the bigger b is, kind of the steeper that that graph goes up, like that. All right, so they all kind of look the same, like this. All the ones that have positive a and b bigger than 1, they all they're all increasing, right, as they go up like this. All right, next up is when a is positive and b is less than 1. By the way, I forgot to mention, right, that this situation here is the function that models exponential growth, and later on we will talk about exponential growth models. And so this one, the next one, where a is positive and b is in between 0 and 1, right? Essentially what that does is it reflects the graph around the y-axis, right? And you get this situation here. And that is called exponential decay, that situation when you have that. So here I'm going to make b in between 0 and 1. Okay, so you can see there's 0.7. Again, the a still controls the intercept, like that. Okay. All right, and then the next two are when a is negative. Remember, if a is negative, what that really does is reflect the graph around the x-axis, right? So the exponential growth one was where it kind of went up like that, and this one would be the exponential growth graph reflected right around the x-axis. So here's where the a is negative. Let's put this up here. And then if we switch the a to be negative, right, it switches the graph so that it's down here. Okay. So if I change it to positive 1, right, that all that does is reflect, around the x-axis. If b is in between 0 and 1, then the graph looks like this. That is the graph of, and the exponential decay flipped, right, are reflected about the x-axis again. So that situation would look like this. Here's where the a is positive, and if the a is negative, right, it flips that graph right around the x-axis there. All right, so you can see they all look similar, right? They all kind of have that same shape. Again, the b, the bigger the b is, the steeper this thing goes up or down, depending on which case you're looking at. Okay, in this section, they want us to evaluate some exponential functions without using a calculator. All right, so let's take a look at how we would do that. Remember, evaluate just means to plug in, right, the number that they tell us. So in this case, they're wanting us to plug a 2 into the function f of x equals 1/3 times 6 x to the minus 2. All right. Okay, so we would plug the 2 in for x. All right, and then 2 minus 2 is 0. Anything to the 0 power is 1. And 1 times 1/3 comes out to be 1/3. Okay. All right, next example. They give us f of x equals -7 times 2 to the 4x minus 1. And they want us to plug in a 0 into that. Okay, so -7 times 2 to the 4 times 0 minus 1. So that's going to be -7 times 2 to the 0 power minus 1. Right, and remember the order of operations. Say you would do the exponent part first, right, before these others. So 2 to the 0 power is just 1. Then -7 times 1 is -7. And then -7 minus 1 is -8. All right, next example. In this example, they give us a function, an exponential function, 2 times 5 to the x minus 4 power, and they want us to evaluate this at 2. All right, so again, just plug 2 in for x. I get 2 minus 4. All right, so 2 minus 4 is -2. Remember the rule for negative exponents, right? Says that that is the same as (5 to the minus 2 power is the same as 1 over 5 squared, right? So 5 to the -2 is the same as 1 over 5 squared. Uh, 5 squared is 25, right? So we get 1 over 5 squared. And so then we need to multiply 1/25 times 2. Remember, you can always change the 2 to a fraction. And then just multiply the tops and the bottoms there. So you get 2 over 25. All right. The next type of problem is, and these problems, what they'll be asking for is finding the exponential function given some information about it, right? So it says the graph of an exponential function has a y-intercept of -5 and passes through the point for -80. Find the exponential function that describes the graph. Okay. All right, so the y-intercept is -5, and it passes through the point for -80. Okay, so we know the format of the exponential function, right? It's f of x equals a times b to the x. That's what we're looking for. Okay. Also, right, we know from what we were talking about before that this a is the y-intercept, right? So we know we are given that the y-intercept is -5, so that will just flat out be a 5 right there. Remember, that has to be the y-intercept, okay? If it's not the y-intercept, then it's a different type of problem. Or you have to do different steps to get there. All right, so we figured out what the A is. Now all we need to do is to figure out what the B is, okay? So how do we do that? Well, what we would do, right, is to use this point, okay? So basically what this point says, right, if this point is on the graph of this function, that means when I plug in a 4, right, in for x, I am going to get negative 80. So that's exactly what I'm going to do. I'm going to plug in the 4, right, in for x. And I'm going to get this equation right here, okay? All right, so I plugged in a 4. Then, because this point is on the graph, right, this says what you get when you plug in a 4, which is f of 4, right, in function notation, is equal to negative 80. So this thing right over here is equal to negative 80. So replace that by negative 80. And now I have an equation that I can solve, right, to get B, okay? Okay, so the first thing I want to do to solve an equation like this is to isolate this B over here, right? I want to get B to whatever power it is by itself on one side of the equation. And the way that I would do that is to divide both sides by negative 5. All right. So over here on the left-hand side, I have negative 80 divided by negative 5. That's going to be a positive 16. And over on the right-hand side, I'm going to have B to the 4th power, okay? All right. So I've got the B to whatever power isolated by itself, right, on one side. What I'm going to do is to take the 4th root of both sides, okay? Oops. All right, and when you take the 4th root of b to the 4th, all right, that's just going to come out to be b, okay, for us. There is a little point that I'm glossing over there, but this is just what you need to do here, right? And so now I need to figure out what the 4th root of 16 is. It's going to come out to be 2, right? Because if I take 4 2's and multiply them all together, it comes out to be 16, okay? So now the question is, well, how would I find what that is, okay? Well, you can use your calculator, right? If you didn't know offhand that the 4th root of 16 was 2. So also, you know, if here 16 is a perfect 4th power, right? So the answer came out to be 2. But there's plenty of numbers, right, that are not perfect 4th powers, and in that case, you're going to get a decimal as the answer. That's perfectly okay. You just need to know how to find that in your calculator. So how you would do it, your calculator might have an nth root key, but if it does not have an nth root key, what you would do, right, is just plug it in like this, right, your scientific calculator, and then to the 1/4 power, okay, 1 divided by 4. And you can see I get a 2, right, as the answer right there. Okay. So you might have to do it that way. To me, that's an easy way to do it on just a regular scientific calculator. Okay. All right. So we got b equals 2. So now what the final answer is? The final answer, right, is the function, the exponential functions equation, right, formula, whatever you want to call it, which is going to be minus 5 times 2 to the 4th power, okay? The A we figured out was negative 5. The B we figured out was a 2, okay? There's an easy way to check that and graph it out and see if it goes through those 2 points. So let's do that. So minus 5 times 2 to the x, and I noticed that I wrote down a 4 right here, but it should not be a 4. It should be an x, right? So the final answer is negative 5 times 2 to the x, okay? All right, if I graph that and look at that function, I can see it has a y-intercept, right, of negative 5. And if I go out to 4, I'm going to have to zoom out a lot, right? And let's see. Let's just go from minus 5 to 5. All right, and look, and the point was 4, comma, or was it 16? Let's see, what was the point they gave us? 4, negative 80. Okay. All right, and you can see there's that point right there, and the y-intercept, right, is going to be 0, comma, minus 5. Which is right here. Okay. All right. So again, right, this is the answer here. All right, next example. In the next example, we have the graph of an exponential function passes through the points 1, 6 and 4, 162. Find the exponential function that describes the graph. All right. So very similar problem, right, to the previous one. We want to find an exponential function that passes through those points 1, 6 and 4, 162. All right, we know that our function looks like this. F of x equals a times b to the x, right? We know that a is the y-intercept, but neither of these 2 points are the y-intercept. And how do you know that? Well, because of the fact that the y-intercept, right, the x number is always 0. So the x-coordinate's always 0. And so neither one of these are the y-intercept. So what do? Well, what we do is just plug each of these pairs of points in. So on the first one, right, or let's just go with this one. If I plug in a 4, right, into this equation, I get f of 4 equals a times b to the 4th. And I know that f of 4 is 162. Okay, because I know this point is on the graph of this function, right? And so that means that when I plug in a 4, I get 162. So this f of 4, that is the number you get when you plug in a 4, so that has to be 162. I'm going to do the same thing with the other point. I'm going to plug in a 1. So I get a times b to the 1. In this case, right, I know that f of 1 is 6, right? So I get 6 equals a b to the 1 power. Okay? So I have these 2 equations involving the variables a and b. What I'm going to do, right, is to divide the equations right here. So I'm going to take 162. Let me just move this one over here. It's easier. And it's easier to think about this equation being on the top, right? The one with the bigger exponent being on the top, all right, when you do this. So that's normally how I like to do that. And so I'm going to divide both sides like this. All right, so I'm going to take 162 divided by 6. I'm going to take ab to the fourth and divide by ab to the 1. Okay. All right, so 162 divided by 6 is 27. All right, over here on the right-hand side of this equation, I have a divided by a. That's going to come out to be a 1, right? And then I have b to the fourth divided by b to the 1. So I'm dividing like bases. When you divide like bases, you need to subtract the exponents, right? So that's going to be b to the 4 minus 1. So I get 27 equals b to the third. Okay. And so now we're kind of in a situation like we were before. What we're going to do is take the cube root of both sides this time. We'll get a b over here. And on this side, we will get a 3, right? Again, 27 is a perfect cube. If you didn't know that, right, then your calculator might have a cube root button. If it does not have a cube root button, then you would do 27 to the 1/3 power like that, and you can see, right, you'll get a 3 when you do that. Okay. Okay, so that lets us know that this function, right, that we're looking for all right, so this function that we're looking for, now we know that the b is equal to 3. All right, so that's what it looks like. So now the question is, okay, how am I going to find the a, right? So all you need to do is to pick one of these points, right, and then plug that point in, plug the x value in for x, and then replace this side with the y value. So you can use either of these two, it's fine, but obviously, right, you're probably going to use this one because the numbers are smaller, right? So when I plug in a 1, I get a times 3 to the 1. All right, I know that f of 1, right, is the y value here. So it's 6. So I get 6 equals 3a. Divide by 3, I get a equals 2. Okay, so the final answer on this one is f of x equals 2 times 3 to the x power. Okay. Okay, and again, let's just take a look at that and see. You can always check your answers on these, which is nice. So our points were 1 and 6. And 4 and 162. That's 4 and 162, so like that. And then our function was, our final answer was 2 times 3 to the x, right? And we can see that's right on the money, right? If I punch in a 1, I get 6. If I punch in a 4, I get 162. Okay. All right. All right, so that's the last example. So these problems, after looking at this video and seeing how these problems go, you should be able to do this Newton assignment, evaluate and write exponential functions Newton assignment. All right, so that's it for this video.